Hello everyone. I'll be talking about controlling classifier bias with moment decomposition, or MODE for short. The key idea is that an unconstrained classification model can be very powerful, but it doesn't necessarily have any guarantees on fairness or protection from bias. And there are many methods to regularize the classifier in such a way that it is unbiased. In general, people are interested in looking at decorrelation from some protected feature, potentially at the cost of some classification power. Today we propose a new technique called MODE for moment decomposition, which allows us to control the dependence on of the classifier on the protected feature in a way that compromises the least between this idea of bias mitigation and classification power. So we're going to be looking at the bias problem in the context of a bump hunt, which I will define in a second. But first, note this famous plot in the particle physics community that shows the excess of signal events that are consistent with the Higgs boson. The key property to note here is that the signal forms a bump hunt on an otherwise smooth background. We refer to the process of finding this excess as a bump hunt. The basic idea is that we search for statistically significant signal peak in a smooth background. Of course, it is required to have a reasonable understanding of this background, or at the very least, the smoothness assumption needs to be valid. But we will see that this assumption can break down quickly if you're not careful. More specifically, when using various machine learning techniques to throw away the vast amounts of uninteresting background, we can introduce artificial peaks that invalidate the smoothness assumption, which means that we basically cannot perform the usual statistical test to check our hypotheses. We need an unbiased way of performing the signal background classification task. Here's an example of simulated data where the signal, which is a W boson jet, which is localized mostly around the W boson mass, and the background, which is composed of jets from other various QCD processes. But in practice, it turns out that there are orders of magnitude more background events than there are signals, which is why we would like to use some machine learning technique to remove as many backgrounds as possible to make the search easier. However, when you train a classifier, let's say a neural network, in a naive way, then you get something that looks like this. This is the distribution of background events that pass the selection, or in other words, false positives. And it seems that the classifier learned that W jets live in this particular mass region and now assumes backgrounds that live there are signals as well. And indeed, this peak is exactly the signal peak. Of course, the background smoothness assumption is not valid here, and you absolutely cannot perform a bump hunt. This is an even worse problem if the peak was just a product of choices you made in your simulation. In that case, you would lose the ability to find signals that are localized elsewhere on this mass spectrum. And what is the solution to that problem? Switching back to ML lingo, we're interested in making the classifier fair with respect to some protected attribute, in this case m, for mass. And as a fairness metric, we will seek to achieve equal false positive rate across mass bins. To do so, we try to produce a classifier whose output S is completely independent from M by adding the following regularization term to the usual loss, where L mode is the integrated quadrature difference between the conditional CDF, denoted as Fm of S, and its zeroth order Legendre decomposition. We can show easily that this criterion is minimized when the CDF of outputs conditioned on M is the same as the marginal CDF, which of course means that S and M are independent. So let's take a look at how this method performs on the previous data. The blue histogram on the right is again backgrounds classified as signal, and the lines on the left represent the false positive rate as a function of mass for various true positive rates. We can tweak this lambda coefficient that represents the trade-off between classification power and decorrelation, and as you increase lambda, you can see that we achieve less biased models, and maybe perhaps at the cost of less classification power, but we have some guarantees about smoothness of background and robustness against out-of-sample data or signals that are localized elsewhere, for example, let's say at 200 GeV. But can we do better? The answer is yes. Independence is a very strong assumption. For our purposes, background smoothness only requires that the model's output is weakly correlated with the protected feature. We can allow for, say, linear dependence on mass and still have a model that produces a smooth background. And one can extend this to higher orders, which would increase classification power. Here's the same example, but here we increase lambda to require more and more strict linear relationship between output and mass. While the resulting background is different from the initial distribution, it's still smooth and introduces no localized features or peaks in the mass spectrum. And now we show how the background distribution for mode regularization at various orders, 0, 1, and 2, as well as disco and adversary, which are other decorrelation techniques used in the field. And none of these produces an artificial peak in the background. However, we're interested in seeing which one is actually doing better in terms of rejection power. So we plot the signal bias, which should be 0 or roughly less than unity if the classifier produced an unbiased sample. And for values larger than unity, the classifier introduces a significant amount of bias and the results are essentially unusable. The x-axis is a measure of classification power. And we can see that the flexibility beyond decorrelation provided by mode 1 and 2 translates into roughly a 20% increase in rejection power. Finally, we know that mode allows unprecedented levels of control over the dependence on the protected attribute. In this plot, we show how linear models which use mode 1 can be tweaked to change the strength of the linear dependence, or the slope. And we also show how you can change mode 2 to be monotonic across your protected feature. For more details, check out the paper on the archive or the GitHub repo, which has implementations for mode both in TensorFlow and PyTorch.